Okay, this is going to look at testing a binomial distribution as a model, which is really quite similar to the work we did last lesson on testing a Poisson distribution as a model. So yeah, shouldn't seem too challenging, hopefully. This is the example from your online textbook, which, having looked at it, is slightly peculiar, as you'll see. But anyway, we'll do it. So, number of girls in a family of 5 children. So, if you add up the frequencies, n is 100. So, 100 families with 5 children in were sampled, and then the number of girls is noted. And it's suggested that the distribution might be modelled by a binomial distribution. Give reasons why this might be so. So these reasons are pretty consistent. We've been talking about them quite a lot. So we've got 2 independent outcomes. So certainly for this, a baby will be a boy or a girl. And there's a fixed number of trials. I'll change my pen in a minute. So there's 5 trials. So we're basically looking to see whether X can be modelled with binomial 5p, where p is the probability of success. If you test at the 5% significance level whether or not it's binomial with p at 0.5, it actually doesn't fit. But I'm going to run through a test where we estimate p from the table, and it will come out as being a bit different to 0.5. So maybe, I don't know, the families come from a certain area where the probability of being a girl is slightly lower for some reason. I'm not quite sure why. But you can see the distribution. It's got this unimodal shape. It's quite symmetrical. It's just, there's quite a bit more going on at 0 than there is. Well, yeah, it just looks a bit heavy on the left-hand side of the distribution, doesn't it, for p to be 0.5. So this works very similarly. So the null hypothesis is that it's a good fit. So the binomial distribution is a good model. So a binomial distribution is a suitable model. And then the alternative is that a binomial distribution is not a suitable model. And another model would be better. So this is quite in line with all the hypothesis tests we've done, really. So to estimate p from this table, we need to find the mean. And the easiest way to find the mean would just be to put the table in as a frequency table on your calculators by going to menu 6, 1 variable, and then you get your frequency table and you can just put your values in. And the mean comes out as being 1.99. So the average number of girls per 5 trials is 1.99. And that makes p approximately 1.99 over 5, which is 0.398. So we're estimating P from this sample of 100 families. If you took a different sample of 100 families, you're very unlikely to get exactly the same thing, and that's why P is an estimate. So we're estimating the underlying population probability of success with the sample. So yeah, probability of girl 0.398. I'll leave you to make what you want of that. So estimating P, and this will be true for all the binomials, P is equal to the sample mean divided by n. So sum of the frequencies. Right, so from there we can go into doing the table like we did before. Let's change this board over. So we've got x and the probability x equals x and then expected values and observed values. So x is taking values from 0, sorry, really didn't want to say 1 there, from 0 to 5 because there may be no successes in 5 trials. And to get the probability x equals x, you're going menu 7 on your calculators, and then it's binomial PD option 4, and this time we want a list, and then you can put in your x values down the left hand side, and then if you just press equals on one of them you can put in n as 5 and p is 0.398. Remember the table truncates, so you should be looking at reading from the bottom so you don't get a rounding error. So I'll just write these in. So 0.0791, 0.2614, 0.3456, 0.2285, 0.0755 and 0.01. And then expected values, so this is a probability of getting no girls in, but we need to times that by 100. So 7.91, 26.14, 34.56, 22.85, 7.55 and 1.00. The expected value here is below 5, so we need to combine these two together. When it was Poisson, you would have had to have done the probability x is greater than or equal to 5 here, if you remember, to get this expected value, because Poisson is an infinite distribution. Because the binomial finishes at 5, then this here is just the probability x equals 5. So just be careful of that with Poisson. And now we're on greater than or equal to 4. Expected value is these two added, so 8.55. The observed value is the 2 added for 4 and 5, which is 11. And then the other observed values were 13, 18, 38 and 20. So it's not looking bad, it's not looking amazing, it's not looking bad. So yeah, see what happens when we run it through. Degrees of freedom. So we've ended up with 1, 2, 3, 4, 5 rows. and we need to take off 1 for the total of 100 and 1 because we estimated P from the table. If you were given P, you wouldn't take this one off. And then the critical value for 3 degrees of freedom at 5% is 7.815, and you can read that from tables, so you've been doing a bit of that already. And if you remember what that means, it's the value over here, so the probability of being to the right of that value is 5%. When you find your test statistic, so your chi-squared test statistic, so that's the sum of observed minus expected squared over expected. I'm not going to do that, I'm sorry. You get 7.22, and then I need to compare that with the critical value of 7.815. Because it's closer to 0 than the critical value, you accept the null hypothesis. Remember, if you're at 0, the observed and the expected would meet exactly. And then the further you go this way, the worse the fit is to the model. So because it's closer to 0 than the expected value, you accept the null. So a binomial distribution with P equals 0.398 is a suitable model. So hopefully that all feels okay. If you could look at doing, so it's exercise 6D, which is on page, just find it. It's page 110 of your online textbook. It's the red FS1 textbook. So page 110, exercise 60, question 9, then question 4, and then question 5.